dive into chirality in liquid crystals. And I'm not going to talk about chiral pneumatics because you've already heard a lot about chiral pneumatics. I'm sure you'll know more about chiral pneumatics. So basically, I'm going to focus on chiral smectics. So the Smectic C star and the nanophases are together. So we use in a very sort of imprecise way these same Schoenflies point groups to describe the symmetry of liquid crystal phases that we use to describe in a very rigorous way the symmetry of rigid molecular structures. So these are the symmetries of various phases. So the Smectic C and the Smectic C star, from the point of view of what I'm going to talk about now, are probably the most important ones. So the Smectic C, you've got a C2H means there's a twofold rotation about an axis perpendicular to the screen, and then a mirror plane in the plane of the screen. So if I take this trans tube butene, or I flip it 180 degrees and reflect, I end up exactly where I started. And over here, you have a C2, but no reflection. So this molecule is chiral, this one's achiral. Okay, so, well here, this is my take on what liquid crystals are. I told you the liquid crystals are the same thing as molecules, and I actually believe that. So, molecules are a collection of fundamental particles, atoms, basically, caught in wells on a free energy hypersurface, configurational hypersurface. And there's a lot of motions that are available, and the energy can change, and you're bouncing around among these different energy wells. But then there's these barriers you can't get over, right? It's those barriers that you can't get over, so you can't access all the conceivable configurations. That's why you have molecular chirality in general. And I think liquid crystals are exactly the same thing, but not all the atoms are covalently attached. So it's just a supramolecular assembly, and you have to have a certain volume to have, you've got to get rid of the surfaces basically to have the properties of the phase. And Noel taught me this way of thinking. It really resonated for me as a chemist, and I figured I would share it. So if you plot free energy versus temperature, okay, so the free energy is, the enthalpy of formation, H minus T times the entropy of formation. So the free energy involves both enthalpy, heat formation, and also entropy. So, if you have a phase sequence like this, each of these, you can do this with molecules. You can also do it with phases, okay? So each of these phases has an entropy and enthalpy of formation. You plot G versus T, then the slope is minus S, minus the entropy. So if you have a big negative slope, that's a high entropy. Okay? And the intercept here at absolute zero. Okay, so this is a fantasy, this is an oversimplification, but the intercept here is the enthalpy of formation. Okay, so you plot temperature versus free energy, and the intercept is enthalpy, heat of formation, and the negative of the slope is the entropy of formation. So you have these phases, okay? So here's a phenylpyrimidine. It has this nice INAC phase sequence that is very attractive for many reasons, and the isotropic is always the highest temperature phase. And then you go down from the isotropic, you get these other phases. Well, what that proves is that the isotropic has to have the highest entropy. The highest entropy phase is always going to be the one that comes out, that's the global free energy minimum at the highest temperature, because it has the steepest slope of this line. Okay? So at the high, see this red line here, the iso, at all these temperatures above T and I, the isotropic is the global free energy minimum. It has to have the highest entropy experimentally. That's true, right? If it's the highest temperature phase, it has to have the highest entropy. And it has some intercept up here, it has an enthalpy of formation. So then you go into the pneumatic phase. The pneumatic has less entropy, it has a lower entropy, so the line is less steep. How can you see the pneumatic? Well, it has to have a more favorable enthalpy of formation. So it's this trade-off. As you cool down, the enthalpy becomes more important relative to the entropy, and these lines have to cross only if the pneumatic has lower entropy and lower enthalpy. Then the lines cross, and in this range here, with this green line, the pneumatic is the global free energy minimum. So it's like an isomerization, but it just happens by changing the temperature. Okay, you're changing the structure, you're going to an isomer, But it just happens by changing the temperature. And then you get this nanophase segregation that leads to the formation of the smectics. So, you have aromatic core that is more polarizable than the aliphatic tails. So, well, first of all, why is it that you get a pneumatic? Why does the pneumatic have more favorable enthalpy of formation? It's easy with these short rods. It's not true with long rods, but with short rods, it's easy to see that going from here to here is going to cause entropy. Right? The pneumatic has less entropy than the isotropic. Okay? Less random. Okay? So that must mean that something about the pneumatic phase gives it a more, sort of more favorable heat of formation, enthalpy. Okay? What could it be? Well, I think it's van der Waals. No, I don't think anybody really knows for sure, but I think it's just dispersive attractions between the rods are better overall. These are collective free energies. This is a collective free energy of an ensemble. It's not a per molecule thing. Okay? So there's a huge, huge numbers. And the temperature range over which these things can exist at equilibrium, room temperature is 0, infinitely narrow. Okay? Because the free energies are so huge. Okay? So what is it about the pneumatic that enthalpically favors it over the isotropic in this temperature range? Well, it's the more favorable dispersive attractions, I think. So if you just say, well, the polarizable aromatics are going to have much stronger attractions, van der Waals attractions than the aliphatics. So when you go to the smectic, where you get this layering, these lamellar phases, right? Nanophase segregation of aliphatic sublayers and aromatic sublayers. So that puts the aromatics in a sublayer. That also favors dispersive attractions because the aromatics are more polarizable. That pays the entropy cost of going into the smectic, I think. Okay? And then you go to the smectic C. So there's always this question of why do the molecules tilt in the smectic C? It's a lamellar phase where all the molecules are tilting off the layer normal, locally in the same direction. Okay, so why does the smectic C tilt? Okay, this is just an argument. This is not experimental fact. We know the smectic C has, sort of lower entropy and better enthalpy than the smectic A experimentally. Okay, the smectic A has to have higher entropy, but we don't know exactly why. So here's a proposal. The tails are melted. They take up a lot of area per molecule projected onto the layers. So that means they want a lot of space, right? That sort of tends to pull the cores apart. So the distance between the cores is not the optimum van der Waals distance, say. And you pay for that with entropy from effectively free rotation around the long axis and higher symmetry and maybe some other stuff that we don't understand. This phase has to have higher entropy than this one. Okay? It has to, experimentally. That's true. Exactly what entropy that is, you're just speculating, okay? At least at this point. All right, so then why do you get this tilt? Well, if the cores tilt and the tails don't tilt, then the cores get closer together and they can get to their optimum van der Waals distance, and the tails keep their area per molecule, and everybody's happy, and you get the smectic C. But you did go to a lower symmetry phase. Okay, this has a C infinity axis above the vertical axis. This one is C2H. Okay, so you went to a lower symmetry phase, and so it costs entropy to go to the smectic C where you have this uniform tilt, but it's paid for by the better, spacing between the cores, better dispersive attractions. That's what I think.
Can't you measure this with X-rays, for example?
I don't think you can see the alkyls separately from the aromatics. That would be great if you could do that. You can see silicons on the end of the tails. There's various things that you can't see in the edge. And Davidov, there's this guy, I can't remember his first name, but he had this paper, where it looked like he was actually distinguishing the cores from the tails in the X-ray. But all he was really doing is measuring the X-ray layer spacing and showing that, when the molecules tilted, the X-ray layer spacing went down in such a way that it looked like the tilt was smaller than the optical tilt, and he assumed that the aromatics were dominating the optical tilt. So, and I've never, know the people that really know X-ray tell me you cannot see the aliphatic separate from the aromatic. That would be great if you could do that, but I don't think you can. So it's all speculation, but, this part looks pretty solid just because of this X-ray layer spacing versus optical, X-ray tilt versus optical tilt. The aromatics dominate. So the optical tilt is always, except in the debris, instead of there's special cases where this isn't true, but usually the optical tilt is larger than the X-ray tilt. And we interpret that to mean that the tails are less tilted than the cores. Okay. All right, X-ray tilt just comes from the layer space that you measure in the X-ray. All right, so there's this phase transition. You pay for the lost entropy by more favorable enthalpy. Somehow, and I just gave you a proposal now. Okay, so look at the Smectic C. What's the point group symmetry here? Well, it's exactly the same as the symmetry of trans-2-butene. It's C2H, two-fold rotation, and a mirror in the plane of the screen. All right, so that symmetry means the dipole moment has to be 0 and the molecule has to be achiral. Or the phase has to be achiral. So then Bob Meyer actually told the story of exactly how this happened back when he got the Buckley Prize, and maybe 10 years ago. And then he told it again at the Gordon Conference 2 weeks ago, so I kind of have it in my head. Unfortunately, I don't have time to tell the story. It started with the twist bend phase, which he was speculating on, and now in the last few years, people think actually exists. Okay? But where he came was the following. If you have a Smectic C, so here's a Smectic C, here's the layer planes, and then the tail's less tilted than the cores, here's the molecules, here's a projection of the molecules on a Smectic layer plane here. So you have the layer normal, and the average long axis, the director, and you're tilted by some tilt angle, so you got this cone. Molecules can be anywhere on this cone, but locally they're all tilting in the same direction. And so then you have this two-fold symmetry axis going along this arrow here from front to back, and there's a mirror plane in the plane of the screen, C2H. So then Bob says, well, what happens if we make the molecules chiral? Okay. Or as he said, chirally asymmetric is what he said, which is not really exactly right. He should have said chirally dissymmetric. Anyway, so what happens if the molecules are chiral? Okay, well, you kill any reflection symmetry in any phase that has chiral molecules that are anumerically enriched. I mean, it's impossible to have reflection symmetry in a phase of chiral molecules. Because if you make the mirror image, it's not the same. You lost the reflection symmetry. Okay? So that means that the Smectic C, you break the symmetry down to C2, from C2H. And you did this by just synthesizing or isolating some chiral thing and using it to make the liquid crystal. So that's all you need to do is to use chiral. Well, this is symmetry breaking by synthesis, right? It's not spontaneous. You made that happen, which is kind of nice because you have control. Anyway, so you break the symmetry down to C2. Now that means there's only one two-fold rotation axis. Now, one of the nice things about C2 symmetry is it's polar. It's a polar symmetry, meaning that molecules with C2 symmetry have an electric dipole moment. Okay? And a phase with C2 symmetry also should have a macroscopic electric dipole. Okay? And that dipole comes from the chirality of the molecules, and in enantiomers have equal magnitude but opposite sign of this macroscopic dipole. Okay, so we define the sign of the polarization as if you're looking at the dipole moment using the physics convention from minus to plus, if that dipole is along Z cross n is along the dipole, P, then that's right-handed positive, and the mirror image molecules would have exactly the same magnitude of this dipole, but it would be opposed to Z cross n. So if this was, this was right-handed molecules, then if you suddenly replace the system with all left-handed molecules, then that arrow would be pointing out instead of back. And a racemate has exactly 0 macroscopic dipole because the molecules just kind of, then you have reflection symmetry again. If you have a racemate, equal parts of both handedness. Okay, so Bob says, well, this is kind of neat. It's a relatively non-viscous fluid with a permanent macroscopic electric dipole in the absence of any applied electric fields. Okay, and they were able to prove this. He and Patrick Hilaire and some other people showed that that this polarization actually exists. And then Noel Clark, who's going to be here on Wednesday, and Sven Lagervall, came up with this idea that if you have a cell with glass plates, here the glass plates are in the plane of the screen, and you put these molecules in this cell, and you treat the surfaces so the molecules want to be parallel to the surfaces of the glass plates. Okay, then if the molecules want to be parallel to the surfaces and the thickness of this thing is thin, and all the molecules in the bulk kind of just follow along with what the surface is doing, then you have only two stable states, right? in the bulk, absent any surfaces, the molecules can be anywhere on this cone, and the polarization just follows around because it's always along Z cross N. Okay? But if you tell the molecules they have to be in the plane of the screen, then you have this state, and that's all you can have. Okay? So here, the molecules are tilting right, and the dipole's going back for positive polarization. Over here, the molecules are tilting left, but you're not changing the handedness of the molecules, so the dipole now has to be pointing out. Still Z cross N along Z cross N. Okay? So there's this coupling between the, the azimuthal orientation of the director and where this macroscopic dipole is. And in a cell like this, there's these two states. Okay, now those two states, here's one with the polarization sticking out. Here's the one with the polarization sticking back. Sorry, this is out and this is back. This is this one. And here's this one. And they're in these wells. This is free energy versus configuration, meaning orientation on the cone. Okay, so you got these two wells that come from the surfaces. And this barrier comes from the fact that molecules of the surfaces want to be parallel to the surfaces. Okay? So these are degenerate states. But if you put on an electric field, on a liquid of dipole molecules with dipole moments, not very much happens. Because there's just too much entropy you have to overcome to really orient them along the field with a high order parameter. But in this case, you go over a threshold. Once you get over a certain threshold, everybody flies over into, no matter where it starts out, you put on a field, there's this enormous electrostatic free energy gain by having the polarization parallel to the applied field, and everybody flips over to here. So we're here. Okay? Now if you make this halfway thick and you've got this large birefringence, so the halfway thickness is about 2 microns, then you basically rotated the optic axis of the phase plate so that it's oriented like this. Okay? Now if I take the field off, everybody's stuck in here, they can't get out because of the surfaces. If I put a field of opposite sign on, the barrier's there, the field goes up and up and up, and finally, boom, everybody flips over. Okay? So now everybody's over here, where I've rotated the wave plate through 45 degrees if the tilt angle is 22.5. Okay? And then I take the field off and they're all stuck there. And so this thing is behaving exactly like a solid state ferroelectric, with hysteresis and everything. But it's actually not just the polar fluid, it's a combination of the fluid and the solid substrates that makes it act like a solid state ferroelectric. But still, it acts like a solid-state ferroelectric, and the switching speed is much, much faster than what you can get with pneumatics normally. This is viscosity divided by the torque, polarization times the applied field is a characteristic frequency related to the time it takes to switch between these two things. Okay, so and this is very fast. Okay, so you have this very fast switching bistable electro-optics, and people thought that was interesting and figured out ways to actually utilize this. So if you take one of these samples of liquid crystal, instead of 2 glass plates, you have one ITO glass plate and one CMOS DRAM chip. And you put aluminum mirrors on the surface of the chip and connect them up through vias to the memory locations. And you stick the ITO at -2.5 volts, and this is 5 volt CMOS, then a 1 is going to put plus 2.5 volts on the liquid crystal, and a 0 is going to put minus 2.5 volts on the liquid crystal. You run this thing in reflection, so this thickness of this film is only a quarter wave, okay, because it has to pass through, the light passes through twice. So then you shine light on this thing, it bounces off this little mirror that can be like 5 by 5 microns or something, or even smaller, and then it comes out to your eye, and you end up seeing what looks like color. If you use time sequential color illumination with red, green, and blue LEDs, you run them really fast. You can actually get full color, full motion, full color images by running these things at like 10 kilohertz. So the frame rate is 10,000 frames a second. Your eye just sees all these colored dots coming in and converts it into a moving image. And so you've probably seen these things and didn't know it. This is a it's a viewfinder chip manufactured by Miyota in Japan, and we made a run on rear projection high definition television in 2000. So this is here you have to use a different chip for each color, and just to get the brightness up, use a beam splitter and then combine the things back. And this thing is a 0.78 inch diagonal, 2 million pixels. Okay. And so you can make a really nice HDTV 720p. It's basically, this is a 720p HDTV on 0.78 inch diagonal. Okay? But you have, this TV is a microscope, basically. So, you're bouncing light off the chip and, reflecting it up onto the screen with a mirror, and you've got some lenses in there, and you blow that thing up to 50 inches diagonal. And it's like a high power microscope. So if there's any defects in there, you're toast. But, unfortunately, you could make enough of them to get them into the stores and let people order them and get all excited, and then, but then, the manufacturing lifetime issues ended up killing that project. But now, there's all these viewfinders and various, infrared beam steering using this guided wave geometry, and then you can use these things as write heads for holographic memory, and you can also make pico projectors. So I have one right here, and I can try to show it. Let's see what happens. So this is a this thing has a pixel density. It's like 16 million pixels per square inch, but it's only about a quarter inch diagonal. So it's got some millions of pixels. Let's see, I have to get the app. Okay, so this is this is totally phony. There's no color there and there's no motion, right? It's just a bunch of red dots and a bunch of green dots and a bunch of blue dots. But you're cycling through them at 10,000 times a second, and so you get this perception of color and grayscale. It really likes to have a very dark room. This is so cool I have to show. Let's see if I can let that help. The issue is that it's LEDs, right? So, the LEDs just don't, they're not bright enough. Okay, but and there also aren't enough gray levels. But it looks like a motion, full motion video. So, here we're blowing this thing up from a quarter inch diagonal. It's got the same pixel resolution as an iPhone, which is like 960 by 5 something pixels. Okay. So. Okay, so that is happening because of the chirality of molecules. I mean, this thing, this projector, you can get it on Amazon.com. It's called iPico, and I don't get any money. Okay, so this thing, well, it's, its LEDs just aren't bright enough, but still, I think, it's fun. So so basically this is possible because of the chirality of molecules. It gives you this very, very fast switching, high stable electro-optics. And so you can make something that you can show to an audience like this. But I haven't figured out any other application. Although really this is for social media, so you can take movies and pictures on your iPhone and show them to your friends without having to patch your iPhone on. That's their plan. Okay, so all right, so there are actually applications of chirality in liquid crystals right there, other than the twisted dimension. And here's one that involves ferroelectric liquid crystals. All right, so now we get to a real stereochemistry story. This is a cool story of chirality. So I love Charles Mogan, and I would love to discuss this, but the bottom line here is that you have an achiral nematic between a pair of mica plates. And Charles Mogan showed that if you rotate the top plate, this was in 1911, this was published, if you rotate the top plate relative to the bottom plate and put plane polarized light in, it will just follow the optic axis of the top plate and come out rotated. And that's called Mogan following because of Charles Mogan, and we still call it that today, and this was one of the two inventions that made liquid crystal displays possible in the beginning. Of course, in 1911 it was a little early, so you didn't get to see that happen. But, this is a chiral structure. Right? You've got this twist, right? I mean, the nematic, and actually, Mogan actually realized that the director had to be moved. They had no idea what liquid crystals were. But he intuited that the optic axis was making a smooth helix. Something was pinned at the surfaces of the mica plates, and when he rotated this thing, the optic axis made a smooth helix, and it's a wave-guiding phenomenon, and the light comes out rotated. Okay? And pretty amazing, this guy. So, okay, so this thing is a chiral director structure. But is the phase chiral? The phase is not chiral. I mean, surfaces can give you chirality. You see chirality all the time in liquid crystals because of interactions with the surfaces. Like you have a liquid crystal droplet. It's almost always chiral, right? You know, because the director is trying to figure out how to deal with the surfaces in a spherical droplet, and ends up chiral. But that does not make the phase chiral. And there's lots and lots of papers where people make this mistake. They see a phenomenon that's coming from the surfaces and think that the phase is chiral. Okay? In particular, people have been searching for chiral phases from achiral molecules forever. Okay? Just like, well, not like Pasteur. I mean, it's possible that you can get a chiral phase from achiral molecules, but that hadn't been seen until relatively recently, actually 1996. So these bent core things were first synthesized by Forlander at Halle in Germany. Back in the 20s, he was synthesizing zillions of liquid crystals, and he made these things. And back in those days, it was either yes, it's a liquid crystal, or no, it isn't. So he said, yes, it's a liquid crystal, and published a letter, like 1 paragraph long, about this. And that was in 1929. So then, Hideo Takazoe and Junji Watanabe, this is Junji's daughter, at the favorite songbar. They both have great voices, and he does too. The guy Junior just wiped out with these people. But they're incredible. And this is Karsten Church, of course. I don't know if you know him. He's a fantastic chemist. And so Hideo and Junji started looking at these bent core things and putting electric fields on it. What they saw was that this thing was behaving like some of the bent cores, not this particular one, but some of the bent cores were antiferroelectric. They were behaving like they were polar. And the molecules weren't chiral, and this started off this whole banana mania thing that's been going on since the Kent State International Liquid Crystal Conference in 1996. Yeah. So this particular compound, after the banana mania hit, and people were looking at these bent cores, Gerhard Pelzel and Wolfgang Weisflog, Forlander was storing all of his samples in vials and cigar boxes in the chemistry building. And he was long dead. And they got a new chemistry building. Pelzel and Weisflog were working there. And so they rescued all his samples in these cigar boxes and brought them over to the new building. And they went back and found this compound and determined the structure of the phase and published it in 2001. So the molecule was synthesized in 1929, and the phase was determined in 2001. It's kind of cool. Okay, so what's going on here? Well, this gets back to Pasteur's, resolution, okay? Up until Hideo and Junji did their thing, no chiral liquid crystal phase from achiral or acidic molecules was known. And in fact, there are a lot of papers where, you start with an achiral nematic, and then you do some chemistry or some reaction with polarized light or something, circularly polarized light, and you're looking for tiny amounts of chirality. You create with your circularly polarized light. You do that by doping your stuff into a liquid crystal and showing that it's a twisted nematic, or it's showing that it's twisted. Okay? So, the observation of a chiral liquid crystal phase basically was taken as proof that the molecules had to be enantiomerically enriched. There was no way you could get an achiral phase without having chiral molecules. Sorry. There was no way you could get a chiral phase without having chiral molecules. That was just the conventional wisdom. That was the dogma. Everybody thought that. It was a rule, right? Just like RNA cannot be catalytic, right? That was a rule in biochemistry until Tomchak proved it could and won a Nobel Prize. Okay, so in this case, it turns out that these bent things are definitely achiral by our definition, right? Every conformation is chiral. There's not a single achiral molecule in there, or hardly any, and yet they're all in dynamic equilibrium with their mirror images very fast, conformational motions. So you have this bent core thing that's achiral, and yet, it was showing this kind of electro-optics that made it look like it was ferroelectric. And then in 1977, Knoll is the liquid crystal Pasteur. He's not here, so I can say this, right? He's like Pasteur for liquid crystals. He looks in the microscope and sees things that no one else sees. It's kind of miraculous. And he still does this. He was doing it last week. Okay? So, literally. So, he looks in there and he goes, oh my God, there's these two chiral domains. I've got right-handed domains and left-handed macroscopic domains in the sample of this achiral molecule in this little crystal phase. And so that was the first fluid conglomerate in history, right? You know, these molecules spontaneously segregate into right-handed and left-handed domains. Okay? And, okay, so this came from the electral optics. And so this is a 4-micron cell with, ITO plates, so you can put on an electric field. So we're driving this thing with a 1 hertz, smooth, triangular field. You know, so it ramps from -5 volts up through 0 to +5, and then down and down. And you can see that the system is responding fairly dramatically. That shows you that it's got to be ferro or anti-ferro, or there's some kind of spontaneous polarization. And if you look at this domain right here, these exchange, okay, this is a cylindrical focal conic, so the layers are perpendicular to the substrates in nested cylinders. Layers are in cylinders, nested cylinders perpendicular to the substrates. Okay? So when these brushes are rotating, that basically is telling you what the molecules are doing in those layers. Okay? And if you look at this domain, from one side of the field, the brushes rotate counterclockwise. For the other side of the field, the brushes rotate clockwise. So the field is going back and coming out. And the sample is responding by rotating counterclockwise and then clockwise. That means that this has to be a chiral, the domain has to be chiral. Because if you have a clock, when I shoot an electric field perpendicular to the clock face, how does it know if this rotation is supposed to be clockwise or counterclockwise if it's not chiral? You can't know. Okay? So this means that there's chirality. Now, it could have come from the surfaces, but okay, so a huge amount of work later, it's not from the surfaces. Okay? It's really a chiral domain. Okay, so if you're going to get right-handed domains from an achiral molecule, then you got to get left-handed domains too. Okay? So if you look at this domain up here, it's the mirror image of this one. Right? So they're going like this. For the same side of the field, when one goes clockwise, the other goes counterclockwise, and vice versa. Okay? So this is a fluid conglomerate. Okay, and this domain is the mirror image of this, and the same as that. Okay? So this is a fluid conglomerate with these chiral macroscopic domains that came from achiral molecules in this case. Okay, so here you're getting chirality from magic, seemingly. Breaking this dogma that existed up until 1996. That you had to have chiral molecules to have a chiral crystal phase. And out here you see achiral electron-optic center. So exactly how that's happening is, So what's going on here is this thing is actually anti-ferro. Okay, so this is an anti-ferro. Okay, so in an anti-ferro phase, the ground state from layer to layer has the dipole going back and coming out from layer to layer. So it alternates back and out from layer to layer. So there's no net polarization at 0 volts, 0 field. But the layers are polar, and so if you put an electric field on, then you drive this thing to one of the ferroelectric states where all the dipoles are pointing in the same direction. Because it's this electrostatic free energy gain for having the polarization along the applied field. You take that field off, and they relax back to here. You put a field of opposite sign on, they flip over to here, take the field off, and they relax back to here. So this is monostable. The ground state is anti-ferro. And then there's these two ferro states that you can access by putting on electric fields. Okay? These two states are degenerate, but they're pointing in opposite directions. Okay, so where's this chirality coming from? Well, if this is the molecule, we think it looks like a bow and arrow. Okay? So the molecule itself is the bow. Okay? The director is the bow string. The average long axis of the molecule is a 120-degree angle up. Average long axis of the molecule is vertical, so that's the bow string. And then the polar, the twofold symmetry axis of this thing is the arrow, of the bow and arrow. Okay? So now if I take this structure and I rotate it so the arrow is pointing straight at you, okay, the bow is still bent back, but in projection it just looks like a vertical line with that arrow pointing right at you. And if I rotate the other way, then the arrow is pointing away from you. Okay? So these are just two sort of orthographic projections of this object that allow us, to think about what the structure might be. Okay? So what's going on is, it is a smectic. You can tell in the actuator. The molecules go into layers, and they're tilted. It's a kind of Smectic C, but in order to fill space, well, that's a hypothesis. Okay. The fact is that all the arrows are pointing in the same direction. Okay. So if the molecules tilt right and the arrows are all pointing out, I think, you know, they're all in the same direction to, you know, to fill space, right? And, you know, it's, you know, when you have these bent things, they want to be parallel. All the arrows want to be pointing in the same direction. Okay, so they can tilt right, and you know, or they can tilt left. So over here, if the arrow is pointing along z cross n, then we call that positive. Just positive chirality. It's just invented. You know, just made it up. And then if the polarization is pointing opposed to z cross n, so here z cross n would be pointing back on this side. So if the arrows are pointing out, that's negative. So this is negative, this is positive. These things are chiral by the non-superposability definition. Now this is a fluid, right? So this picture is way too static. Makes it look like a crystal. It's not a crystal, it's a fluid. But this captures the symmetry of the system. So you cannot superpose this on this. If I just slide this thing over, then, you know, then they're tilting in opposite directions. That doesn't superpose. Okay? If I rotate this thing so that the arrows, you know, if I rotate it so that they're tilting in the same direction, then the arrows are pointing back instead of out. Okay? So these two structures are non-superposable mirror images. Of course, this is the mirror. Okay? So this molecule spontaneously creates these large domains that you can easily see in the light microscope that are either all the layers are like this, or all the layers are like this, or other things can happen. Okay? But that's basically where the chirality is coming from then. It's okay, so well that's operationally where it's coming from. Here in a little more detail, it turns out the ground state is antiferro. Okay, so in the chiral domains, if you have one layer where the arrow is going back and tilting left, and the next layer the arrow's tilting out and the molecules are tilting right, the arrow's coming out and the molecules are tilting right. Okay, so these two layers both have the same handles. I could have asked a quicker question about that, but instead I'll just tell you. These two layers both have the same handles. They're both negative. The arrow is opposed to z cross n. So these layers are tilting in opposite directions. Polarization is pointing in opposite directions. They both have the same handedness. So if you have a stack of these layers alternating like this, that's going to be chiral, unichiral. Okay? And so if I put on an electric field, one of these layers flips so that I get the dipole along the applied field. If I take the field off, I go back to here. Put opposite side of the field on, and it goes like this. So this is this chiral domain. Here's the cylindrical focal conic. Here's looking right down the cylinders. This is what the molecules are doing. Because of the tilt, the average optic axis is vertical in the antiferro state. Okay? If I go to this ferro state, the brushes, if I rotate the molecules clockwise, the brushes go counterclockwise. Because you get the brushes, the extinction brushes, where the molecules are parallel or perpendicular to the polarization, which is vertical. Okay? Well, you know, the polarization is vertical and the layers are going around in these circles, and so you have to rotate around on the focal conic to get to extinction. And then if I put the field of opposite sign on, it goes to here. So that's the electro-optics in the chiral phase. So this is the left-handed version, and you also have a right-handed version that behaves enantiomerically. Okay? And, right. So what about these achiral things? This is achiral electro-optics. There's nothing chiral about the electro-optics going on over here. By the way, it's possible to fill the whole cell up with this or with this. You can go either way. How? Yeah. Okay, so this phase and this particular stuff is monotropic. So on cooling from the isotropic, it's all this. But if you keep cooling out of this phase into what's called the B4, that happens at lower temperature, the B4 is chiral. So then if you heat from the B4, which goes all the way to room temperature, and people thought it was a crystal. If you heat from the B4, the whole phase is chiral, the whole thing is chiral. It's a metastable chiral liquid crystal phase. It comes from melting a chiral phase at a lower temperature, that comes in at a lower temperature.
It's like a nucleation point.
Pardon?
Just like a nucleation point. You start with.
I don't think it's like nucleation. The nucleation happens when the B4 grows. So if you keep cooling this thing you cool it down to like 150, and the whole sample turns into B4. I wish I could tell you the story of the B4 because it's a gorgeous story about chirality, but I don't think we're going to have time. But the B4 is chiral, so everything turns into this chiral phase. Okay? Then when you heat up, you're starting from the chiral phase, you heat up into this phase, everything's chiral. But then if you drive it for a while, it kind of goes back to the achiral phase because that's the thing we're going to do. And this, of course, is why nobody else noticed that it was a chiral phase, because they were always cooling from the isotropic, and they were never seeing the chirality. But, you know, Noel, I'll give you a trick. And I've seen Noel do this many, many times. What he does, he doesn't look at the phases. He always goes to the transition and just goes up and down through the transition slowly over, you know, and spends a lot of time in there looking at the transition. The transition down from the isotropic or up from the crystal, which turned out to be B4. That's why he saw the chiral phase and nobody else did. So don't always just cool. You know, you see these phases, right? And when you hit a phase transition, stop and just kind of wiggle up and down with temperature and watch the phases grow in, you know, and see what's going on. That's what the pros do. Of course, you would have to be like Pasteur as well, but other than that. Okay, so, all right, so that's, you know, so how do you get this achiral phase? Well, it's synclinic. All the molecules are tilting in the same direction, but they're changing sign. They're alternating, you know, the sign of the chirality. Okay, so this layer is right-handed, Z cross N pointing out for this layer. This layer is left-handed, right-handed, left-handed. So if you have alternating right-handed and left-handed layers, it's achiral, right? I mean, the phase is achiral if the layers are alternating right-handed and left-handed. So this is an achiral antiferroelectric phase. And when you put a field on, it turns into this, you know, achiral ferroelectric phase. Okay? For one, you know, so let's see. And notice that the birefringence with the field on in the chiral phase is the same as the birefringence with the field off. Yeah. I mean, this is turning green with field on, and it's, you know, and it's purple with, let's see. Yeah. This one is purple at zero field and green with the field on. This one is green at zero field and purple with the field on. The birefringence colors are the same because the structures are so similar, right? You either have this, okay, so if you look at this layer interface, and the molecules are tilting right here and they're tilting left on the other side of the interface, we call that anticlinic, or, you know, opposite tilt. Okay? Anticlinic. Clinic means tilt. Okay? And if they're like this, where they're tilting in the same direction from layer to layer, this layer interface is synclinic. Okay? So if you have a synclinic structure, whether it's ferro or antiferro, it's going to have the same birefringence. And the same is true of the anticlinic. And the anticlinic has a lower birefringence than the synclinic. So looking at the birefringence was the key, really key issue right now.
So this is not a mixture of two molecules, just molecules, the bow. The bow you described is pointing either into the screen or out of the screen.
Right, so these dots are the arrow, and the bow here is tilting, is kind of back, right? Here, you know, the bow looks like this, right? Here is looking at it parallel to the plane, right? You know, perpendicular to the best plane of the bow. This is defined by the two lines on the bow, okay? So then if I rotate it like that, now it's looking straight at you. The arrow is pointing straight at you. So if someone is aiming a bow and arrow, and the arrow is aimed right at your eye, the bow is going to look like a straight line of projection, right? But then if they rotate it like this, then you would see that it was a bow, okay? So that's what we're looking at here, is the bow is bending back and the arrow is pointing out. And over here, the bow is like this. The bow is coming out and the arrow is pointing back. But these things have exactly the same birefringence, of course. Well, you know, an anticlinic, whether the bow is, you know, the arrow is pointing out or back, it doesn't affect the birefringence. Okay, so you've got this syn and anticlinic. So we actually, so this is kind of a chemistry, stereochemistry thing. So we have this concept of stereogenic elements, which is okay, this will just take a minute or two. stereogenic elements like chiral centers and sort of double bonds and various things. We call them stereogenic elements. They're Euclidean geometrical features that lead to isomers. That lead to stereoisomers. They're called stereogenic elements. So there are 3 independent stereogenic elements, each of which can have 1 of 2 possible states. Okay? So you can have, now what we're looking at here is the relationship between adjacent pairs of layers. Because that's the difference between these phases, is what's happening in adjacent pairs of layers. Okay? So the adjacent pair of layers can either be homochiral or heterochiral. Those are pairwise descriptors for the same handedness or opposite handedness. Okay? So the adjacent, since the molecules are achiral, and you're getting this achiral phase, the layers can be either handedness. So you can get adjacent pairs of layers can be opposite handedness, or they can be the same handedness. Okay? So there's 2 possible states here, homochiral or heterochiral for each adjacent pair of layers. Then there's synclinic or anticlinic, again, 2 possible states. And then there's relative polarity ferro or antiferro. Those are independent. So there's 8 possible different isomers of this phase, of these phases. This is the B2 family of bent core phases. 8 possibilities. But you only see 6. Why do you only see 6? Here's the 6 phases that we're seeing. We're seeing this achiral phase, the synclinic antiferro, and then we're seeing, these 2 in antiumeric, anticlinic chiral phases. There's these 2 synclinic chiral phases, and then there's this achiral ferroelectric phase. Okay, so what happened was the mirror image of this. See, there should be 2, 4, 6, 8. But you only see 6 because there's a degeneracy, because 2 of these phases are achiral. And then these 4 are chiral, right? This pair and this pair. So you see a total of 6 possible, out of the possible 8 isomers. And this is the B2 family. We have these synclinic antiferro, anticlinic antiferro, synclinic ferro, and anticlinic ferro. Okay? So that's the 4 the 4 basic phases, and then you have the mirror images, except for these achiral ones. The exact same thing happens in molecules, and when you have an achiral phase that's made out of chiral layers, or when you have an achiral molecule that contains chiral elements, we call that a meso compound. Just to confuse everybody, because it's like a mesophase. But, it's the same word, but it means something different. Meso compounds are chemical compounds with multiple stereocenters that, that have an internal mirror plane. You can have a molecule with a right-handed stereocenter and a right-handed stereocenter, and it's chiral. But if you have the same molecule, if it's got, if it has a left-handed and right-handed center, there's mirror center, and it's like that. And that's all the time we have. So thanks a lot for paying attention. It's been fun.
Time for questions?
Yes.
When you have electric field applied to these phases, you always have it's not just switching of polarization, switching of planes as well.
Sorry,
And the electric field
in an electric field in these bent cores?
Yeah, particularly with CS, PS, or these combinations of this, so you have some kind of preserving of chirality. The chiral phase is always the same.
Okay, lots of things can happen. When you put on, originally in the original banana phase, when you put on the field, then, the molecules would always rotate and maintain the chirality. So in the switching, the chirality was always maintained. Molecules start out like this, then they would switch, they would be like that. Okay, so the direction of the polarization is changing, the tilt is changing, the chirality stays the same. But then, it turned out that depending on the frequency, you could actually make them rotate around the long axis. And there are some molecules where the angle is bigger than 120, they really like to flip the chirality. Instead of rotating around the cone, the molecules just stay on the cone in their tilt and just flip the direction of the arrow. That's flipping the chirality. So you can see this chirality flipping or not, depending on the frequency and the specific compound.
More questions? So let's thank